just to refresh your memory from yesterday and the other day, we have a differential eigenproblem, and we are trying to find these eigensolutions. Here, what happens is that we get infinitely many eigenvalues, and then corresponding eigenfunctions, okay? And where n is an integer index, okay? Integer index. And so we have solved a couple of problems. If you remember, I'm not going to go over them. And so final point that we stopped was this this conversion to a SL form, right? Now, conversion to an SL form is, let's say that you have an arbitrary equation in arbitrary form. Clearly, the question is how you convert this into this form, right? If you can do that with some multiplication factor, and then you will be done. And so that's what I'm explaining here. It turns out that P is actually P, which comes with the Sturm-Liouville definition, is can be computed by using the two coefficients, and so on. Okay, and I solved a problem with this, right? We solved this problem. Originally, it is not in SL form, right? Not in SL form. So we cannot identify PQ, cannot identify PQ and omega. But by using that procedure, we can actually convert it into SL form, right? This is the associated SL form. And now we know that P is e to the minus 2x, Q is 0, and the weight is e to the minus 2x, okay? And why is this important? Because, you know, we obtain these eigenfunctions here, and we want to test the orthogonality. So they actually come out to be orthogonal with respect to this weight, okay? So that's your weight. If you remove this weight, you lose the orthogonality, okay? So that's why this is important that you identify the weight, okay? Anyway, so that's a simple example for you to note. All right, now I am going to go through this now. This is today's topic. And now what I want to know is this. I have a question to ask, okay? We have this orthogonality property, which I attach so much importance to it. You will see later when we solve PDEs. This orthogonality will be a lifesaver, okay? A lifesaver. So that's why I want to know what property of an SL operator brings orthogonality. You know, I mean, is this magic or is it really a mathematical reality? First of all, what I want to do, I want to define my Sturm-Liouville operator for this purpose. Okay. Now, if you remember above, I use this form, which I use L for it. Where was it? Here you go. You see, I use this as my operator, right? Which is this. And so now what I do is I just divide by this to the other side with a minus sign so that this becomes plus, okay? And I'm going to define this as my Sturm-Liouville operator. Okay. Now, this is just a minor readjustment. Okay. So that's where this is coming from. You see, there is this piece here added to it. All right. Now, what I want to show you is this. What property? Well, it turns out to be the property is the symmetry property. Okay. It turns out to be symmetry. Now, how do we define symmetry? Okay. So to answer to this question, it is the symmetry property. Okay. All right. Now let me give you an analogy here. Okay. Rn analogy on the notes. Now, if you have a eigen problem, consider the eigen problem Ax equals lambda x. Okay. This is from Rn. All right. So this is n by n. And this is 1 by 1. Okay. Now, and assume where A is symmetric. Now, you know the definition of symmetry in matrices, right? It's equal to its transpose. Okay. Now, if you consider, let's say, consider two. Let me make my analogy clearer here. Okay. Consider two different eigenvectors. X n and xm, let's say, okay, corresponding to lambda n and lambda m respectively. Okay, because if this is not a degenerate case, we expect n many eigenvectors and eigenvalues, right? Okay, then I'm going to do this. I'm going to take the operator A operating on xn. Of course, what does it mean? It means this, i.e. Axn is equal lambda nxn, right? And Axm is equal lambda mxm, right? Okay, so two different. M is different than M. Okay, so let's form this. Form the inner product. Axn with xm. Right? This is a regular inner product. You know, there is an algebraic way of writing inner product. We can write this as Axm transpose xn, right? Just like multiplication here. I mean, it makes sense, right? Let's check. This is n by 1. This is n by 1, right? And when you take the dot product, of course, you get a 1 by 1 operation, right? And so, but this is the transpose, so this is 1 by n, and this is n by 1. So clearly it is 1 by 1 if you consider matrix multiplication, or you are actually multiplying vectors. Okay, so this is the algebraic form of dot product. Okay, and then you know, transpose can be opened up. Right? It can be opened up in this way. So that is the transpose of the product. Okay. And then if you continue your argument, what you're going to get is this. And so let me collect my thoughts. Okay, so this is then transpose. Now we have symmetry, right? We have symmetry. So this A can be replaced by, A transpose can be replaced by A, xn, okay? And so what we get is xm dot A xn, right? By the same analogy, okay? Now what is this? This is, of course, xm dot lambda n xn, right? And what we have started with, okay, let me get rid of this because I forgot to write this equality here. What is this? This is equal to lambda n xn dot xm, isn't it? Right? So now if you started with this and you end up, let me see, this is m, right? All right, I'm just mixed up. You see the morning. This is n and this is m. Sorry about this. And so this is n, and this is m. And then you have what? You have n and m. So let me just change all these, okay? I just mixed these indices up. Okay, and so this is this, and this is that, okay? Now if you subtract, what do you get? You get xn, there's a dot here, xn dot xm, right? And lambdas are scalar. As a factor, you're gonna get lambda n minus lambda m, isn't it? Equal to 0. Because I put this on the other side. Okay, now what does this say? It says this. If this is different than 0, which we said they are distinct, right? This has to be 0. i.e., the eigenvectors are orthogonal. i.e., distinct eigenvectors, distinct eigenvectors to a symmetric matrix A are orthogonal, right? So this is a fact that we know from linear algebra, right? Okay, so now I'm going to use the same analogy here. Now, what's the inner product? You see, I use A, if you look above, to start with, I use AXN dot XM, right? What's the analogy of this? It is the operator operating on phi n and weighted inner product with M. Okay, remember we define the inner product in function space, okay, as an integral, okay? So here is the definition. Let me take you there so that you make the association, right? That was our inner product, remember? This is called weighted inner product. So this is the analogy, okay? So in linear algebra, you have this in Rn, and this is in function space. in function space S, whatever this S is. Okay. All right. So that's my starting point. Okay. So now let me take you there, and now you appreciate the reason. Okay. Okay. All right. Now, so that's the inner product that I'm starting with. Okay. Now I use phi n and phi m here, which are the eigen functions. But let's do it for arbitrary u and v. Okay. And if you continue this process, okay, so which means this is your LU, this is your V, and this is your weight. Okay. Weight is fixed. Weight is always there. Okay. Now, first thing, if you just simplify this, W's cancel, first thing first, okay? So you end up with this, and then you integration by parts, okay? So what I'm trying to do is this. I place U out, V in, okay? And which means it takes double integration by parts, okay? Because this is there is a second derivative here, so you have to do integration by part twice. Now, if you do that, you end up with a boundary term. And now this is what? This is, if you put a weight here, and then divide by the weight. So this becomes your operator operating on V, right? U and V change places. And this is your U already, and this is your weight, which is this, okay? So which means starting from the operator on the left-hand side, I end up with the operator on the right-hand side, okay? So this is actually known as Lagrange identity. This is actually telling us that the SL operator is symmetric, okay? So now you can use this idea if you choose phi n and phi m as the eigenfunctions, which means when you operate with L on phi n, you're going to get lambda and phi n. If you operate on phi m, these are the eigenfunctions. So now if you take this difference, see, which is actually what? What is the Lagrange identity? Lagrange identity says, if you put everything on one side, what do you get? LU V weighted minus U LV weighted equal to 0, right? That's what it says. Okay, so that's what I do. I replace U here and V by phi n and phi m. And same here, this is U and this is V. Okay, and I end up with this, okay, which is complete analogy, right? Complete analogy to Rn case. So this tells us that if lambda n is different than lambda n, the inner product of these two different eigenvectors must be 0. Okay, so that's orthogonality. So everything boils down to what? Boils down to this part, which is on the left, can be put into this form, which is on the right. Okay, which is the Lagrange identity. Okay, so here's the definition for you. If in the process of taking this operator to the other side, if operator preserves the shape, okay, preserves the shape, it's the same operator. This is called star operator. This star operator is called adjoint operator, okay? Adjoint operator. If it turns out that your adjoint operator is same as your original operator, then we have self-adjointness, i.e. symmetry, okay? All right, so we don't use symmetric in function spaces. Symmetric is only reserved for Rn. For function spaces, we use self-adjoint. I call it formally because what happens is You see, I didn't mention that the boundary terms, by the way, become zero. Okay, by the boundary conditions. What boundary conditions I'm talking about? The boundary conditions in the definition of Sturm problem, right here. Let's call this star. On page 2. Okay, star on page 2. By star on page 2. We can show, okay? These boundary terms become zero. Okay, because I'm assuming U and V satisfy the boundary conditions, okay? All right, and then, so if you, well, we established that if you have self-adjointness, then the orthogonality of eigenfunctions is really obvious. It comes out, okay? So let me just show you. You see there are two, you see this formula here? Let me put a question mark under this. You see, because if you remove this formula, you only have self-adjoint, okay? Formally means you have, formally we don't consider the boundary conditions, okay? But if you consider the boundary conditions as well, let me give you with an example here. I think it's best if I explain this with an example. Take this operator, simple operator. It's nothing to do with SL, right? It's just an operator here. Well, it is something to do with SL, but we don't need to know that yet. And these are the boundary conditions. Boundary conditions number 1. And that's boundary condition number 2, okay? And I go through this process. U and V change places, okay? So you see that your L and L star is the same, right? You see, because L star is also they are the same. What about the boundary conditions? Now, if you look at these boundary conditions, now U0 doesn't appear here, okay? But U prime 1 appears. So U prime 1 doesn't appear. So how can you have this 0? If you have, you see, we don't know U1, right? We don't know this. That's not given. You see the boundary conditions? It's not given. U prime at 0, we don't know this, right? It's not given. But we can make some assumptions, okay? The assumption is this. Because we want this to be 0, okay? And this must be 0. And this must be 0. Okay? So which means your L star comes with B stars, okay? B stars, which means the boundary conditions for the star problem, okay? Star problem. It turns out that boundary conditions for star problem is these, because it is very, very necessary that you want the boundary terms to be 0, okay? For BC terms vanish, right? Because you don't want to carry this boundary terms around. If you look at U's only, you don't have these values available to you because boundary conditions are not given in this form for U. So you have to make an assumption for V. So I use these assumptions, which actually constitute the star boundary conditions, okay? Now, if you look at this, your operator is the same, and your boundary operators are the same. So this is actually called self-adjoint without the formal, okay? Without the formal. It is perfect self-adjoint. your two operators as well as the boundary conditions are exactly the same, okay? But it turns out that sometimes you don't have the boundary conditions the same, so, or the operator is not the same. Take this case. I'm going to give it to you as an exercise. This is your operator, and L star turns out to be this. You see, there's a difference. And I'm going to leave it to you to verify this. And also verify this. So it's a totally L and L star are totally different, so not self-adjoint. Okay. All right. Anyway, you can just study this problem. This is just to show you if you have a general. So the question I ask, what conditions on A2, A1, A0 make L self-adjoint? Okay, that's what I'm asking here. All right, because I'm starting with the general form. Okay, and what I'm going to do is this. I'm just going to form this as usual in a product. I'm not using a weight here. It's weight 1. And if you go through this integration by parts procedure, that becomes your L star V. And I assume boundary terms are 0. Okay. So assume these are all 0. Assume made vanish. Okay. Whatever the way you do it, we assume there. It's not our concern. Okay. So this is your L star. Now, if you want L and L star to be the same, okay, so you compare. For L to be same as L star, you must satisfy these conditions. Okay. I just compare these two. I open this up. Okay. For example, I open this up. What do you get? A1 V prime, A1 prime V. Similarly, open this up. Okay. Expand. All right. Whatever. This is second derivative, so I don't want to spend time on that. You do it. Okay. And compare these two, L and L star. It turns out that the coefficients must be related this way. It just boils down to this. It actually means it is SL form, okay? So if you choose your coefficients to be in this form, it becomes a self-adjoint form, right? So that's actually a SL form. So this is just telling us that this is actually same as this problem, right? So let me put a page number here. Where was that problem that I used? Here you go. You see, I use multiplication factor to convert this to a SL form. So compare this with page 8, okay? Page 8, double star. All right. Compare this with double star on page 8, okay? It's the same procedure, but we have a different objective here, right? Our objective was converting a non-symmetric, non-self-adjoint operator to a symmetric operator, self-adjoint operator. And what should be the conditions on these coefficients? That's what we obtain. That's the only condition, okay? Only condition. There's only one condition, okay? That's very nice. All right, these are some kind of periphery stuff, okay? Not the main problem. just to show you where you are, okay, give you a perspective, okay, because otherwise it just becomes very shallow, okay. When you want to learn something, you want to learn it as deep as possible. So that's what I'm trying to do. Okay, this is actually already done, okay. This was the analogy, the notes, okay. This is the RN analogy. This is which I already done. Okay. All right, that's all. You know, this little pieces that I wanted to give you. Self-adjointness is what makes a cell problem produce orthogonal eigenfunctions. Okay, so it's not magic. There's no magic here. All right, now there are other types of Sturm-Liouville problems, by the way. Okay. Now, previous problem was we call regular problem. Okay. So that's actually regular. Okay. If you go up in my definition, I didn't put it there because I want to focus. Okay. So that's actually a regular case. Okay. So that's one class. There are two more classes. Okay. Two more classes. One class is called periodic case. What is characteristic of this is that your boundary conditions is changed, okay, to this. This is actually called periodic boundary conditions. So I'm changing star on page. What was that page? I used it here actually, right? Somewhere. I use boundary condition reference somewhere. I don't remember where. Okay. Okay. Star on page 2. Okay. Star on page 2. So star on page 2 becomes this. Okay. So you change the boundary conditions of the regular SL to this. Then it becomes a periodic SL problem. Okay. Now what is this? This is actually a ring. Okay. You can think of it like a ring. All right. So that's your starting point, and that's the end point. Start, or you can go other way around. You know, let's use the convention. You know, convention is of course you go counterclockwise, right? So that's your start, and that's your end, which is equal. Okay, it's equal. A and B is equal at A and at B. Okay. What happens is this: the value of y at A and value of y at B and derivatives is the same. Okay. So it's like actually your domain is like a circular. Okay, it's a circle. Okay, but it's not important that you visualize the geometry of this. Actually, we will use this later in polar coordinates for theta. Okay. Example is theta variable of polar coordinates. Remember, in that case, you have 2 pi periodicity, right? 2 pi periodicity. So it means wherever you start, you end up with in the same location. Okay, if you complete a full circle. So you will see this actually when we solve PDEs in polar coordinates, that I'm going to use periodic SL for the theta variable. Okay, and there is another one, which is the singular Now, singular means this. P, remember P. If you go to the regular case again, quickly, you see we had a condition there. I hope I put it down. Yes, here we go. You see this? What makes this regular? Okay. Makes the problem regular. Because that's a leading coefficient, right? P is the leading coefficient. Because if you open this up, what do you get? P, y double prime, and P prime, y prime, right? So P is the leading coefficient. So if leading coefficient never vanishes, that's a regular problem. But if you allow the leading coefficient vanish, then you are in trouble, okay? What is the trouble? Trouble is at the point that P vanishes, you have singularity, okay? All right, so that at endpoints, P can vanish, okay? So P, or possibly the weight, which is not our concern here, P is our concern. P vanishes at one or both endpoints. So if you consider the open interval, P does not vanish. So we are not looking for P vanishing in the interior at the boundary, okay? So now I can identify three cases, okay? It may vanish at left, it may vanish at right end, or it may vanish at both, okay? Now, what is the difference between these? The difference is this. You remember the regular boundary conditions? You see? So when it does not vanish, you have the regular boundary condition. Okay? Regular. But when it vanishes, wherever it vanishes, you only take boundedness condition. Okay? So you replace the boundary conditions. Okay? So BC at A is replaced by boundedness. Okay? All right? So that's how you read this. And this is very, very important, by the way, because it's the center, okay, the most important part of this. Here, observe that at A, you have no vanishing coefficient, so it is the regular. But at B, BC at x equals B is replaced by boundedness again. Now, what happens if you have both vanishing? So you don't have any boundary condition. You see, no specific BC, right? We don't have anything, just boundedness. Very general, okay? You see, I told you in class, this is what we want actually for numerical purposes, you know? You don't want any restrictions in functions that you work with. Functions meaning the solutions of PDEs I'm talking about. Let's say that you have a PDE and you want to use a coordinate system for this PDE. You know, coordinate system comes with certain boundary conditions built in, right? I mean, the way we generated those Sturm-Liouville eigenfunctions above, they all come with those regular boundary conditions, right? which they satisfy. And then when you use it to represent a function, you want that function also satisfy those boundary conditions. If it doesn't, then you have oscillations, okay? Gibbs oscillations. But now in this third case, you have total freedom, okay? Total freedom. There are no boundary conditions. So your singular Sturm-Liouville eigenfunctions come with no restrictions at the third case. In the second case, comes with only freedom at B, and in the first case, comes with a freedom at A. So this is total freedom, okay? In 3, total freedom, okay? Yuppie. All right, let me put this. Total freedom of representation. Eigenfunction representation, okay?
Hocam bir şey sorabilir miyim?
Buyurun.
Şimdi bir freedom veriyor ama belki garip bir soru olabilir ama hani oradaki
Buyurun.
peki fiziki olsa hani gerçek ya da doğru olduğunu nasıl anlıyoruz ya da anlayabiliriz? Öyle
Well,
bir durum.
we impose the boundary conditions on the eigenfunctions, okay? That's in numerics. You see, when your eigenfunctions come with boundary conditions, which is you don't have any freedom, okay? Then the function space, the functions that you are working with, meaning the solutions to PDEs, must exactly satisfy those boundary conditions, okay? You may say, what's the problem with this? The problem is that if you put too much restrictions, you see, numerically, then you have stability problems, okay? So that's kind of advanced topic. That's why I don't want to go into that. You have
Tamam.
stability issues. You see, the rule of thumb in numerics is that you want to give as much freedom as possible to your numerical procedures, okay? Because if you restrict your numerical procedures too much, you get stability issues. You know, I mean, you have oscillations, and you have seen the oscillations in f of x equals x case, right? Remember this? Let me go up. Remember this case? You
Aynen
see
hocam.
f. You see these signs. Let's call them phi n's. Okay. Satisfy the boundary conditions. What boundary conditions? At 0, at L, they are 0, right? Because that was a regular problem. So they come with a restriction. But if you look at f at 0 is 0, which is okay. But f at L is L, which is not equal to 0. So that's a problem. You see, you may say, how can I have an expansion of f in terms of these? Okay, because there's apples and oranges here. And then you pay the price. What's the price? The Gibbs oscillations, where your function does not satisfy the boundary conditions, right? Where f is non-zero. Okay. All right. So the price is oscillations, and these are non-physical oscillations. They are numerical oscillations. Okay. So that's why you have to get rid of them if you are numerically solving this problem. Okay. So that's why restricting. You see, this is very much restrictive. These are restrictions. But in the singular case here, you have no restriction at all. You have total freedom. Okay. Now, if I, for example, we will see later, Legendre polynomials is the third case. Legendre polynomials. These Legendre polynomials are so popular in numerics because, for example, spectral element method, finite element method, these two big techniques, solely based on Legendre polynomials. Okay, Legendre polynomials, which is actually eigenfunctions of the third case, which means they don't impose any boundary restrictions on the functions that you expand, okay, or functions as solutions to PDEs I'm talking about. So which means any different type of boundary conditions that your PDE comes, you can use Legendre polynomials. Whatever types of boundary conditions that you are working with as a PDE, you can use Legendre. But in the sinusoidal case above, if your PDE does not have the same boundary conditions that these sine functions satisfy, you cannot solve that PDE without oscillations, okay? There will be oscillations. So that's why total freedom is the best, okay? So let me put a triple star on this. Most used SL eigen function types for numerical purposes, okay? All right, so that, let me just stop at this point because if I want to continue, I can spend a couple of weeks on this, okay? This is very fundamental, okay? Fundamental. You know, I mean, you use finite element method, for example, without thinking about it, right? I mean, perhaps you have some package programs, you have MATLAB routines and so on, okay? You don't think about it, but there is a fundamental idea behind it, okay? And same for spectral methods. These days, everything is packaged, okay? So there's a package says, I am solving using spectral methods. You feed in your PDE and you get your results. What is going on inside that black box? You don't know. There is a fundamental idea behind it, okay? So this SL is the fundamental idea. But in SL, what SL? Singular SL, okay? Singular SL is the fundamental idea. Okay, so that's quite deep, okay? Because these days, unfortunately, everything is packaged and you don't know what's going on inside. If something goes wrong, for example, your car, okay? Your car is a package. If you don't know how the engine works, if you don't know what the components are doing in an engine, if your car breaks down in the middle of nowhere, okay? What are you going to do? Well, you're gonna sit down and wait, right? Or maybe you're gonna walk. So, but if you know the engine, if you know the engine components, what are you going to do? You're gonna open the black box, and if it is fixable, you're gonna fix it, okay? Maybe it is something very easy, right? So that's the same idea. People are using these package programs without knowing what's going on inside, okay? If you get some absurd results, non-physical results out of it, you don't know what's going on. Maybe it is something fixable, but you don't know the fundamentals, okay? So my suggestion to you is learn the fundamentals and then use the package program, okay? If you don't want to write a program. If you don't want to bother with correcting programs, writing programs, and so on. But learn the fundamentals, very, very important. Okay, so that's a fundamental, okay? The singular SL, especially is number 3, which gives you total freedom, is very, very, very fundamental, okay? All right, now if you are interested, I can refer you books later, okay? If you want to learn a bit more on these fundamentals. Okay, now let me solve some examples. Okay, up to this point, it is a bit dry, right? Just theory, theory, theory. Let's solve some problems. Now, what I want to solve is this. Now, this is clearly a periodic SL problem. In fact, we worked with this operator before, right? We get sines and cosines, if you remember, as solutions for lambda positive. And I only change the boundary condition. Okay, so let's solve it. At least let me start it, and I'll give you a break. Okay. All right. So this is example on page what page is this? 13. Okay. So we have y double prime plus y equals 0. And we know that this is a constant coefficient problem. And so we get m square. Oops, I forgot the lambda. Plus lambda equals 0. And now we just go through the cases, okay? And don't forget the boundary conditions. Y at, this is of course occurring on what? From minus L to L. On minus L to L. So y at minus L is equal to y at L. And y prime at minus L is equal to y at L. Okay. So let's go through this lambda values. Remember, we sweep through this real line. By the way, this is an SL problem, right? So it's periodic SL. So we expect all the properties to be enjoyed here. So there is this lambda 0, which is the bifurcation points. Now what happens at lambda 0? You get equal roots, right? And m0, sorry, y, m0 gives you 1, right? E to the mx. E to the 0x is 1, so it's just a c1. And so, since we have repetition, the other one is 1 multiplied by x. Okay? Now let's look at the BC now. Y at minus L is C1 minus C2L, which is supposed to be equal to C1 plus C2L, which is actually Y of L. And automatically, we get what? C1s cancel. Okay. C1s cancel. So you end up with 2 C2L equal to 0. Okay. 2 C2L equal to 0. Since L is different than 0, C2 must be 0. First result. C2 is 0. Okay. Let me put a different colors. So you shouldn't think that I'm zeroing it right from the beginning. I'm zeroing it because of this intermediate result. Okay, what about the second BC? Second BC is y prime at minus L is equal y prime at L, right? Now y prime at minus L, you see only C1 left. Okay, so it is 0 actually. And 0 at y prime at L, right? Only C1 left, because only C1 left, right? So where is this 0 coming from? Because I took the derivative of C1. Because only C1 left. It means this boundary conditions, i.e. BC are satisfied for any C1. So choose it to be 1. Okay? Because 1 is always a nice normalized quantity. Okay? So now lambda 0 with the index 0, 0 with y0 of x as 1 is an eigenpair, which this didn't happen before, right? No, this is something new. So you shouldn't jump to conclusion. You see, that's what happens. The problems that I solve, usually lambda 0 gives trivial solution. Okay. So you jump to the conclusion without thinking about it, without doing any work. You say, okay, lambda 0 is not an eigenvalue. Well, you have to test it. Okay. You have to test it because there are cases that lambda equals 0. Even in the regular case, lambda 0 may be an eigen value. Okay. All right, and then lambda negative. To make sure it stays negative throughout my procedure, because I'm going to do a lot of algebra here. Let's make sure we are actually working with a negative quantity. Okay, so what do we have? We have our roots, real roots, minus plus alpha, and you can use, I don't know which one is useful here, which form. Anyway, I'm going to use this, if you don't mind. E to the alpha x, e to the minus alpha x. I don't know which one is better, because you're gonna do the algebra. I'm not going to do it. Okay. So either you can use this or that. Okay. But just show it leads to trivial solution. Okay. Okay, you show it, all right? And let's take lambda positive case. Again, I'm going to make sure it stays positive. And again, I'm going to take alpha to be positive without loss of generality. I can explain this later if you are confused why am I choosing alpha to be positive. Because it doesn't produce linearly independent solutions if you change alpha to negative. Okay. I mean, if you take alpha both positive or negative, you don't produce anything different. Okay. So you get plus or minus I alpha. So your solution is C1 cosine alpha x, C2 sine alpha x. I'm going to give you a break if you just let me finish this example, okay? And so let's look at the BC. Y at minus L is C1 cosine alpha L minus C2 sine alpha L, which should be compared with this. That is equal to Y of L. Now, whatever there are cancellations here, do it. Okay, these two cancels. So you end up with what? 2C2 sine alpha L to be 0. And you don't want C2 to be 0, right? So I'm going to choose sine alpha L to be 0 for C2 to be different than 0. But let's look at the other conditions. Other BC is Y prime at minus L, which is what? You're going to get cosine minus, so it will be C1 alpha sine alpha L here. The derivative of cosine is minus sine. And when I replace L by minus L, there will be another minus sign, so it makes it plus. And then plus cos, so this will be C2 alpha cosine alpha L. Just correct me if I am mistaken. So this is all minus L, right? For plus L, this will be minus. And this will be that, right? Just check if there's any algebraic mistake here. Well, these two cancels, right? And again, you end up with the same condition, which means that condition above satisfies both BC. 2C1 alpha sine alpha L has to be 0. It means sine alpha L must be 0 for C1 to be different than 0, right? Okay, so what's the solution to this? We already know the solution, right? So this is the characteristic equation, which is the same for both. And that produces what? Alpha L must be multiples of pi. Okay? Multiples of pi, n, 1, 2, and so on. Remember, alpha is assumed positive, right? So that's why n0 is not included. Actually, n0 is already included above, right? Lambda 0 case is actually for n equals 0. Remember? Index 0. So we have it. All right, so what do we have? We have alpha n to be n pi over L. By the way, you can also write this as 2m pi over 2L. This is just telling us that we have 2L periodicity, okay? And then corresponding eigenfunctions. What are the eigenfunctions? Well, what was our conclusion here? C2 is different than 0, and C1 is different than 0, right? So which means both cosines and sines survives this procedure. So cosine n pi Lx and sine n pi over Lx comes as two linearly independent eigenfunctions for each eigenvalue, okay? So this is a degenerate case, right? Thus, i.e., there corresponds to linearly independent eigenfunctions for each one of eigenvalues. All right, which is contrary to the theorem, right? Remember the theorem? Let's go up. What was the theorem saying us here? You see here, there corresponds only one linearly independent eigenfunction to each eigenvalue, right? Remember this theorem? But this was the regular case. Now we don't have a regular case here. So that's why not all the results of this theorem is applicable, okay? So just be aware of that. So this is actually called degenerate case, okay? All right. Anyway, what we obtain at the end is this. We obtain 1 cosine n pi Lx and sine n pi Lx, and this corresponds to lambda 0 equals 0, and these correspond to lambda n equals n pi over L square, n, 1, 2, and so on, okay? Now, if you expand, so eigenfunction expansion of f in terms of, let's say, give me a sign here. Okay, let me use this because I use stars, right? Is what? A0 times 1 an times cosine n pi lx and bn times sine n pi lx. N goes from 1 to infinity. Now, do you recognize this? This is the Fourier series. This is the Fourier series expansion of f. Okay? So you see Fourier series that has been around more than a cell problem is around. You see, Fourier derived these Fourier series without knowing this orthogonality idea, without knowing this Sturm-Liouville problem, and so on. Sturm-Liouville came later. But now we make a connection. Okay. All right, I'll give you a break. 10 minutes break. Okay. So I'll see you whatever after 10 minutes pass. Okay.